being here. Now it's on. So yes, I will talk a bit about Tezos, but not just, especially this being the Cornell Blockchain Conference. I try to make it a bit academic, and I do talk about Tezos, but I don't shield. I like to talk about interesting topics, stuff that I would want to hear if I were in the audience. So hopefully you'll find this instructive and interesting. So I'm going to talk about scaling with rollups and sequencers, and I did something clever here with the fonts. You see that the S is not it's slightly great because maybe we just use a single rollup. But what does it mean? Isn't the point of rollups to have multiple rollups? Stay tuned. About me, so I'm an early architect of the Tezos protocol since 2014. So it's been a 10-year journey. My background is in financial math. I work in quantity finance at Goldman Sachs and Morgan Stanley. I did a little bit of robotics and AI. I was a research engineer at Google X and Waymo, and my background in AI is why I can say with confidence a lot of AI blockchain theses are bullshit and created to sell tokens, unfortunately. So Tezos is a blockchain designed to evolve. It has a robust technological foundation. It's serious technology, and it's serious technology that's been improved over the past, over the past 10 years, but also on-chain directly with 15 successful upgrades over the past 5 years. It has advanced developer tools, a really credible scaling roadmap. We're going to talk about that. So it's not the Tezos roadmap. This is a roadmap of some entities around the Tezos ecosystem. A passionate community of builders and users. And so, like I said, we've had 15 successful decentralized upgrades and counting. So we'll start with a rollup refresher. We'll talk about what are sequencers, why use sequencers, what's the catch, a little bit about shared sequencers, and then a Q&A. And the length of the Q&A will be determined by how good I am at pacing myself for this. Let's see. All right, it's about 11:05, and I have until 45. Okay, refresher on rollups. I'll start with a spoiler. Rollups are scaling technology. That's great. They are a great scaling technology. That's fantastic. The downside is that they're only a scaling technology, and that's a discussion I often have. I have the thing is like, oh, but with a rollup, maybe we put an oracle on the roll of it. No. If you can't, if you can't do it on a blockchain, you can't do it on a rollup, right? The rollup is not going to do anything magical for you. What it will give you is it will give you throughput, it will give you scale, it will give you customization. So a lot of these benefits, but it will not do magical things that blockchains cannot do, sadly. But it's still quite nice. So to introduce rollups, let me recap the three main functions of validators. And the word validator has been very overloaded in the blockchain space. It could mean someone who runs a full node. It could mean someone who create blocks. So here I'm talking about specifically block creators. But what do they do? Well, one of the things that they do is that they order transaction. And ordering transaction sounds very boring. Do we really care if this transaction came before that one? Well, actually, yeah, we do. That's one of the most important things in a blockchain. That's how you solve the double spending problem. You solve it by saying this transaction happened first, so that's the one that counts, and the other one doesn't count. So, 99% of the problem is ordering transaction in a blockchain. It provides that availability. It's also say, well, it's nice to know that which transaction happened before, but if I need to accept a payment, I need to know that no other transaction happened before. So the solution in blockchain is we just publish every single transaction. And if we publish every single transaction, we can know every transaction that happened in which order. And as a result, we can check whether or not they're valid. And the third thing they do is that they execute transaction to maintain the state of the ledger. You can query this node and say, hey, is this valid? Like what's going on right now? And if you want to scale a blockchain, the trick is that you need to unbundle all these functions. You need to spread them out. So rollups specifically are about outsourcing execution, and that's what I'll be talking about mostly. So the simple idea for outsourcing execution is to be very lazy. It's just not do it, right? Because you think of validators as like, well, if you validate, it means you have to execute the transaction, right? That's very important. That seems like almost the most important and the most difficult thing in a blockchain, but it's actually the easiest part to outsource and the least important one, because you could very simply outsource execution. You could just say, like, I'm not going to execute anything. I'm just going to do data availability. I'll put the transactions on chain, and I'll just order them. You know, what's the problem of doing that? You run into some problems. One is that you can't really, if you don't know the state of the chain, it becomes harder to get fees, right? If you want the transaction to pay fees, you need to know whether or not they're capable of paying fees. And if you want to know that, you need to have some notion of what the ledger is. And the first problem you have is like the ability to pay fees means like maybe you need to have some sense of the state. But the other thing is, like, you might think, well, if I'm only executing transactions, maybe we could have different full nodes attend to different set of transactions, right? Maybe you're only going to download this transaction, I'll only download this transaction, and we'll execute them. And you can do that. And this is an old approach. You had this in the early days of Bitcoin. With you saw this with projects like Mastercoin, for example. You saw it with projects like Counterparty. They were projects trying to increase functionality on Ethereum, on Bitcoin. And the way that they did this was to say, we're going to have a special set of transaction. We'll have a fold over this transaction. So either a fold over the transaction, or either a fold over the or either a fold over the transaction graph of Bitcoin, or either a fold over the UTX also set of Bitcoin. But it'll get us a state. And the problem with the system, and that's this very, very old approach, which didn't really work, has been recently rebranded as sovereign rollup. So if you hear about a sovereign rollup, that sounds much better than a rollup. It's not just a rollup; it's sovereign. That's so much better. But actually, it should be called an orphan rollup, because the problem with those things is they have a state, and that state can never communicate outside of itself. It can't go back to the main chain. So if you look at those old systems, they would let you deposit Bitcoin into them, because they have some sense of like the events happening on the L1, but you could never take anything out of it, right? Because the L1 cannot understand what's going on, because it doesn't execute those transactions. So the problem, if you try to scale by outsourcing execution naively, is you don't know what's going on. You have this separate states which can't really communicate. You can't bridge between these zones, and they are essentially condemned to stay apart. So how do we solve that? Well, rollups, that's what we do. So the idea of rollups is that to talk to each other, we're going to post a small cryptographic proof, a commitment to the state of these rollups. So now, committing to the state of a ledger, that's something that we know how to do very easily. That's so simple. You know, you have a root hash, you have a Merkle tree of your state, and then you post a Merkle tree of that state, and that's it. You're done. So it's a hash. It's very, very simple. You can do fancier things. You can do vertical commitments, all of this sort of things. But at the end of the day, simple cryptographic commitment, that's not the problem. And then you can have the main chain acts as a communication layer, right? Because if every one of these sub ledgers, or if every one of these rollups can observe the commitments on the main chain, they know this. They can then accept proofs about what's going on in the other rollup, right? So they know what's the latest state of, if I'm rollup B, I know what is the latest state of rollup A, and then someone comes and tell me, look, I have burnt this token on rollup A, so let me mint them on rollup B, and here's a proof because this happened in the state. You can essentially pass messages between those. So you're good, like you have this communication, that's great. The problem is, is like, who poses commitments? Are we going to trust someone to pose a commitment? Can anyone pose a commitment? And the answer is going to be anyone. But how do we know they're correct? And here there are two answers. We are going to know that they're correct either interactively or non-interactively. So if you're doing it interactively, you have what is called an optimistic rollup. So the idea is anyone can post a commitment, and they could post a valid commitment or an invalid commitment. But we're going to play a refutation game where bad state commitments can be challenged. So anyone can commit a state. They say that's the state of this sub ledger, or that's the state of this rollup. And if you disagree with me, come and prove it. So you play challenges, and you do that by bisecting the execution trace. You take the whole execution trace of your rollup, the whole implementation of the state machine of the rollup, and you just replay it. And let's say, for example, that we went through 10 billion assembly instructions in order to go from one state to another. I will say, well, I disagree with you on the billions step. So let's see if we agree on the step at position 500 million. Do we agree? Yes, we agree. All right. Now let's check if we agree on the state at position 750 million. Okay, we disagree. So the problem is before that, and so on and so forth. So you narrow it down to like a single step. You replace that single step on the chain, and voila, you've proven that an execution trace was bad. So they cannot show that a commitment is correct, right? You're not going to be able to prove that you made the correct commitment, because in order to do that, you would have to go at every step, right? Because you could be correct at 99.99% of transitions, and then a single one would be incorrect. However, you can refute incorrect commitments. So the idea is many people make commitments. Some of them are going to be correct. Some of them are going to be incorrect. And if they're incorrect, people will come and remove them from the set of commitments. They will say, no, that's not valid. And for that reason, they carry slashable deposits. The point not being, it's not for economic security, it's just as a spam prevention mechanism. I can't spam the chain with a bunch of invalid commitments. If I do that, people will run machines, they will refute them, and then it will go away. So how do you get security? You wait. Essentially, you wait for the commitments, and if a commitment has been on a chain for a long period of time and no one's bothered to refute it, you just assume it's correct. So that's optimistic rollup. And with validity rollups, it's much simpler than that, and it's also much more complicated than that. You just post a cryptographic proof that the commitment is correct, and you are done. So that's great. You just say, look, you know what? I executed the code correctly, and here's a proof that I executed everything correctly, and you can just run this computation in near constant time, and you'll have the proof. Interestingly, a lot of the proof mechanisms for that are, in some sense, similar to what we described. They involve rolling out the entire execution trace, but then you turn your execution trace into a hologram, and then you do some magic on it, and you get and you get those proofs. So there's pros and cons to both approaches. Optimistic rollups, there's no overhead to execution, right? In your happy path, in the past where no one's trying, where no attackers trying to annoy you or do anything like that. And which is the default state, because if your system works, it's costly for attackers to do that. So if I'm an attacker and I know, look, if I attack this thing, not only am I going to fail, I'm going to lose money, then I'm not going to have attacks. So everything's going to go well, and I'm going to execute code with no overhead. I could be executing assembly code on a machine, zero overhead, and that's fantastic. Whereas for validity rollup, the proof generation is going to cost me something like 1000x overhead. I haven't followed with the data science. Maybe it's 100, 200x. It's still huge. Now, that overhead doesn't necessarily have to be time, because a lot of this proof computation can happen in parallel. So maybe you have a giant cluster of computers, and you're going to be able to compute the proof in the same time as it would take to execute on a single machine. But still, in practice, not really. Like, even if you, the mere fact that you have to implement your proof into a special circuit means that even if you were to execute it without proving anything, the overhead would still be quite large. And on top of that, you had proving time. But beyond time, it's also cost. If the cost in computers of like running 10,000 times or 1,000 times the computation that you need is huge, and parallelization is tricky. Like trying to parallelize 1,000 seconds of computation across 1,000 CPUs into a single one is not trivial. You can use native code directly with optimistic rollups, whereas you have to convert your code into a special mathematical form. Either it's like arithmetic circuits for a snark type of proof, and for Starks, it's going to be algebraic representation. It's not very, very friendly, and also it's error prone. Like, you could make some errors in your circuit. It's very easy. It's very hard to audit these things correctly for the moment. Now, I'm pretty hopeful that auditing the systems and formal proofs about the systems will get better. So I'm quite optimistic on that. I'm less optimistic on the overhead improving much. Now, with optimistic rollups, you have complicated state management and edge cases for challenge. In some sense, on the one is going to have very, very complicated cryptography, but then once you have done all your cryptography, you have a very simple prover, and then you don't have to worry about anything else. With the optimistic rollup, I explained the challenge. There's a lot of edge cases. What happens, if you present like your bisection, and maybe you maybe it's like the last tick. What if it's like a different type of tick? What if it's like the first tick of a computation? What if you have parallel code? All of that. It's easy to get lost into the state machine of these challenges, and it's easy to get it wrong. Whereas in the other one, it's hard to get the math right because it's complicated. But once you get it right, you can kind of like prove that it's right. So one has kind of like this very compartmented complexity, where essentially you could ship your complexity off to someone who doesn't understand necessarily anything about the rollup and just focus on like, is this math correct, yes or no, which is like a simpler answer to give than is this kind of like game theoretical arrangement stable or not. You need a single honest party for safety with rollups. So you still rely on one honest party being able to come in and say, hey, those commitments are invalid. You shouldn't have made these commitments. Whereas for a validity rollup, you need a single honest party only for liveness. You need someone to post a proof, but no one, if there's no honest party online, which is a very, very sad state of affair, then you lose liveness, but you don't lose safety. Block producer censorship can introduce safety faults for optimistic rollup. If your block producers stop including people challenging bad commitments, then all of a sudden those bad commitments are going to be finalized. So that's not good. And again, for validity rollup, block producer censorship can only introduce liveness fault. So again, point for validity rollup. And you have a long withdrawal period, several weeks for the optimistic rollup, again, because you need to wait to see if a challenge has happened. Maybe you want to check like if censorship is taking place, like the defense essentially against block producer censorship in optimistic rollup is you wait, and if everyone sees that there's an invalid rollup that's about to be finalized, and somehow you have a cabal of your block producers trying to hide it, very, very remote scenario. But if that happens, your option is probably to hard fork out of that. Whereas here, your block producer in a validity rollup, they can only introduce liveness fault. You basically have no safety faults if you don't have a bug in validity rollups. So you get near instant withdrawal as a result of that, which is very nice. So I still think optimistic is better. And even though like zero knowledge rollups are very, very popular now, and just to give a little bit of context, I wrote a blog post in 2017, which was called "Why I'm Not Pursuing Sharding for Tezos as a Scaling Technology." And in it, I explained that we had this zero knowledge proofs that were mostly used for privacy, but that their true calling was to be used for scaling. And I outlined how you could scale essentially using something like a ZK rollup. So I have been a proponent of this approach for a very long time. And despite that, I still think optimistic today is a better choice. One, because even though the reputation game complexity is annoying, it can be managed, right? You only need to get it right once. And once you get it right, you have it right. So it's not intractable complexity that's going to stay with you forever. You can actually implement this correctly and be done with it. The overhead of zero knowledge is currently too high and will remain so for the foreseeable future. Like that's primarily the main reason. The 1000x overhead is just really bad. The long withdrawal window, which is one of the main downsides of the optimistic rollup, can be addressed by detecting when censorship is not happening. So essentially at chain level, you can check and you can say, well, if like anyone who's supposed to create the block is creating the block on their order, it means that, either censorship is happening via 99.9% of the network or there's no censorship. But you can actually detect a scenario where you would have 2/3 of the validators trying to censor something. So that actually can give you a lot more confidence, and you can perhaps like lower this withdrawal window from a few weeks to a few hours. And then I guess the long withdrawal is not an issue if everything takes place in a single rollup, right? If I have a single rollup and basically all I have on my main chain is just staking and like transaction fees and data availability, then in some sense I can have, I don't really care about withdrawals because all my activity is happening inside a rollup. I'm almost never withdrawing anything. A single rollup, but wait a second, doesn't that defeat the purpose? So I thought that the whole point of rollups was horizontal scaling. You remember what I said early on? We want to have these different zones. They want to talk to each other, and that's how we're scaling, right? We're scaling because they're all, they're all being computed separately and talking to each other. So if they're going to be talking to each other, if we're going to be exchanging assets between rollups, it sounds like the withdrawal window is super important because you don't want to have a 2-week lag for communicating between those things. And it turns out that no, that's not the whole point. Rollups are awesome for vertical scaling as well. If you want to scale by just having beefier machines and more compute, Rollups is a great way to do it. Why? Well, first you have the fact that a rollup has a single honest party assumption. And that's not the case for consensus. The thing that sucks with consensus is that it has this honest majority assumption, right? So in order of like the assumption you want to have when you develop your system, the best to have is no honest party assumption, right? You're doing a signature, for example. You don't need an honest party. The signature is a signature. That's just cryptography. That's just math. That's the best scenario. The worst scenario is, well, I have a bunch of validators and I think they're somewhat incentivized to not collude with each other, and hopefully they won't do that. That's the worst scenario. And when you hear that blockchains are backed by math or like it's all cryptography and so on and so forth, sadly, the real security assumption has less to do with math and more to do with this very squishy, hard to establish human, hey, are people colluding or not colluding? And then in the middle, you have something which I really like, which is a single honest party assumption. Single honest party assumptions are not really worth sweating. They are very, very good. If the point is like, if there's not a single honest party in the world that cares about the integrity of your ledger, then, what do you care anyway, right? If all your users are dishonest, what is even the point? So I think it's fair to say you can always have a single honest party that's going to be interested in helping the ledgers. So that's a very, very good assumption. But that also means that you can have much stronger hardware requirements, right? If I care about the validators of my chain, if I want to have as many validators across as many countries as possible, I want to have people running full nodes, in the middle of remote areas and communicating by satellite and all of that. Surely I want to have minimal hardware requirements. You can run Tezos today on a Raspberry Pi. You can run Tezos today on a Raspberry Pi over a Starlink connection if you want to. That's kind of nice. With a rollup, that's not the case. I need a single honest party, so I don't really care about the requirement. I could have much, much higher hardware requirements. If it takes a $20,000 machine to run a rollup, that's less of a problem because you don't need many, many people across the world running it. You need one person, or it's more if you have more than one person, but like you need one honest party to do it, and that's it. So that completely changes the trade-offs that you have, and I think that's quite important. It also changes the trade-off in terms of jurisdiction, and that's the thing that's completely missed about rollups. But they are much, much more permissionless in this respect, because you still want your validators running in every country in the world, right? It's annoying if all of a sudden the validators of your blockchain say, well, I'm a validator, I'm running in the US, I have to do X, Y, and Z in order to run my validators. Oh, I'm a validator, I'm running in Europe, now I need to do X, Y, and Z. And very, very soon you end up with like over 1/3 of your validators that have to comply with a certain set of regulations. That's happening. That's going to happen. We've seen, a lot of regulations push on DeFi front ends, and the next thing that's going to happen, they're going to push on validators. Like right now, it's like wallets or broker dealers. It's like, oh, you're a wallet, you're a broker dealer. Next step is going to be block validators. Like, oh, you're a block validator. Hey, say you validated a swap transaction. That's on you. You don't want to live in this world, and the only thing we have is to minimize what validators do. Otherwise, validators will have to hide, or otherwise validators will have to concentrate in a few jurisdictions when they can operate legally, and that's not good. So you want your validators to do as little as possible, and I think that's part of what I'm hoping to see on Tezos is the main validators focus on staking, consensus, data availability. Transaction processing happens in a rollup. That's much more mobile. You need one honest party somewhere in the world running it, and not a whole lot of honest party all running it. Much, much, much better profile. And so, yeah, that's what a lot of talented engineers working on Tezos have been working on. Basically, moving a lot of activity into a single rollup, which can have a lot more throughput. The other aspect, don't get into it too much today, is that if you want to use sharded data availability, right? If your data is going to be spread across many, many validators, you can't really do your execution on a layer 1 because then they don't have access to all the data. Whereas if you run it into a rollup, you can actually consume this sharded data availability. It's a technical point. But basically, you've seen these arguments from like, oh, do we want to have the fragmentation of rollups on the one hand, or do we want to have composability and a monolithic implementation of a blockchain? And the truth is, like, I like monolith. I like having a monolith. I like having a lot of composability. But the best way to do composability is to do it on a single rollup. Way, way, way better than try to do it on L1. It's ways to do it on an L1. So that's the idea behind like something tentatively called Tezos 2. One rollup, ultra high throughput, and support for mainstream programming language. These two things go hand in hand, essentially. Why? Because if you want to support mainstream programming languages, you basically want to support assembly language. You want to support the overhead of like running something very, very granular with your compiled high-level things. So you have to have a lot of, I would say, overhead for compilation. And that means that you need to have a lot of performance. And it's powered by two things. There's a smart rollup engine, which is basically a support for optimistic rollups that's built directly into Tezos since the Mumbai upgrade. So it's not implemented as a smart contract. Today, if you're running a, if you want to run an optimistic rollup today on Ethereum, your options are basically to try to do what Arbitrum is doing, or you can pretend that you have an optimistic rollup and run Optimism, but what you'll have is just like some custodial solution. And you can actually run a real rollup today on Tezos. And the Tezos DAO, which is a sharded data availability layer that essentially provides the backing underneath this. Am I doing on time? Okay. So let's talk a little bit about sequencers. Originally, I had this thing entirely about sequencers, and that was a little niche. But I think it's important because it's a word that's been overloaded a lot, and people have different ideas about what it means, what it should mean, and what it can do. So let's demystify a little bit. So sequencers are a technological solution that can complement a rollup. They are not necessary. They are used for the ordering of transaction within the rollup, and they're a great way to reduce latency. So that's the positive account for sequencers. That's what they are. Sequencers, they're not necessary. By default, if you wanted to do a rollup, you wouldn't have a sequencer. You would just use a base layer. I mean, that's, now they call them, I think the latest like hype word for this are like called based rollups. But that's the thing, is like you post your transaction on a chain and then they just get collected. The idea is that somehow a rollup is intrinsically linked to a sequencer is not false, because historically that's how people were thinking about them at the beginning. They were thinking, oh, wait a second, we could compress transactions, we could like aggregate signatures, but for that we'll submit them to a sequencer will aggregate everything and then put it on a chain, and then I'll have a rollup. So there was a lot of thinking around it, but when you fundamentally see what the rollup is about, it's not really about that. They have nothing to do with posting commitments to the rollup state. So we've seen a lot of projects say, oh, well, the sequencer is also the one posting the commitments. That doesn't have to be the case. That doesn't have to be the case at all. Anyone who follows the data posted on the L1 can post the commitments. That's not the job of the sequencer. They have nothing to do with defending honest commitments, right? We've seen again project where you have a centralized sequencers that they run transaction, they post the commitments. Maybe they allow other people to post commitments, but then they're the only one who can refute them. It has nothing to do with challenging dishonest nodes or defending honest commitments. That could be anyone. And more importantly, it does not allow trustless bridging between chains of rollups. It's very, very popular as an interoperability theme to say that your sequencer is going to make all these blockchains interoperable, is going to allow all these different rollups to talk to each other. And that is just marketing. That's not true. We'll see why. So, okay, so they do certain things, they don't do other things. Why use sequencers? What's the point? Improve user experience by low latency confirmation and access to the speculative state of the rollup. Those are essentially the same thing. Like sequencers are about latency primarily. So let me just explain why they're about latency. So the way this works typically is you'll have a sequencer, you'll send your transaction to the sequencer. Sequencer is going to say, okay, thanks, I'll take your transaction. Now, I have certain privileges with respect to the rollups. They're limited, those privileges. But the privilege that I have is within reason, I get to decide on the order of transaction, right? I'm going to send messages to the L1, and I'm going to have some priority as to how those messages are treated. And that priority helps me maintain a speculative state that says, well, at some point, my message is going to get to the L1. And when that happens, this will be the state of the ledger. Because of that, they can answer immediately when you send a transaction and say, okay, I promise I'll integrate your transaction. And here's the current state. That's great for UX. If you're building a dApp, you talk to a sequencer node. And optimistically, you say, look, sequencer is answering to me honestly, and I can reflect to the user what's going to happen. It doesn't affect security. If I'm a user, if I really care about security, I'm not going to trust the speculative state of the sequencer. I'm going to wait until everything is posted on a chain, and that might take 10, 20 seconds, right? So it's not that long. But if I'm a user and I just want to go through my day, I can have my confirmation within less than a second. And that's really, really good user experience. That's really good developer experience. So what's the catch out of this? What are we losing? So sequencers cannot corrupt the state of the rollup. They don't have access to the state of the rollup. They can't steal assets. They can't do anything. They just get to choose somewhat the order of transactions. They can't censor transaction. Like I said, they can only choose this order somewhat. You could totally have the sequencer share the you could have the rollup share its inputs between the sequencer and the L1. All it has to do is prioritize the sequencer. So the way this is usually implemented is with a thing called a delayed inbox. So essentially, you can pose your transaction to the sequencer. You can pose them on a chain, but on a chain, they will only be executed after a little while, assuming that the sequencer did not pick them up. So you can't censor transaction. You can delay them, right? You can say, look, I don't like you. Maybe your transaction is going to take an hour to be executed as opposed to going through me. So that's one downside. But you can't really censor them. And you can't reorganize the rollup as well. You don't have this power, because what determined that is the L1. At the end of the day, you're still subject to the L1. Now, you could do some small reorganization and trick users via your RPCs, but only for a short period of time. And if they are security conscious, they will check the main chain. So the sequencers really do not have that much power. And that's good. That's good. If they give you like good latency without power, that's fantastic. But what's the catch? So if you have a centralized sequencer, they're going to collect all the MEV, right? They see all the transactions that happen. They pick the order, so they can make a bunch of money like this. So if you have a single party sequencer, they could impose arbitrarily high fees on you, because they get to check, look, you'll have a transaction in an hour if you want. Otherwise, you'll have to pay me. And so they can set monopolistic prices. That's not great. And if they misbehave, that significantly degrades the UX. But the nice thing is you can make different trade-offs, because they don't have to misbehave as well. You can tolerate a lot more centralization in your sequencers than you would tolerate in an L1, for example. So let's talk about shared sequencers. That's also a topic. People have said, oh, with shared sequencers, or shared sequencers that sequencing multiple rollups, you're going to get to have cross-chain interoperability. You'll have transfers. And shared sequencers do not do anything interesting. I'm sorry, they really don't, unless you also trust them to validate the chain, right? So here's how people think it works. You say, okay, I'll have a sequencer. My sequencer is going to sequence rollup A, and is going to sequence rollup B at the same time. Can I build a bridge like this? So I'll send a transaction. I'm going to send a transaction that burns token on chain A, and then mints token on chain B. And I'll send that through the sequencer. And because the sequencer is shared, we're going to have the property that these transactions either both get executed or neither gets executed. So that sounds almost like a bridge, right? Because either nothing happens, or I burn my token on chain A and I mint my token on chain B. So I've done essentially a transfer. Like I have managed to have atomicity of my transactions across two chains. That doesn't get you a bridge. And the problem is that the sequencer needs to know whether or not you're going to be able to burn your token on chain A. Like if I have no tokens left on chain A, then maybe I can't really burn them. Right? It's still a valid the sequencer could inject those two transactions atomically. You can have the guarantee that it's going to be atomic. However, what's going to happen is they're going to say, well, yeah, it was atomic. You burn your token on chain A. Oops, sorry, you didn't have any tokens on chain A. That transaction failed. And the sequencer knew. So you have to trust the sequencer essentially to do a bridge. The sequencer has entire discretion to mint tokens this way, or to burn token this way. The sequencer can steal funds. The sequencer can arbitrarily steal funds in this thing. So now you don't have this kind of like nice trusted sequencer that wasn't going to do anything. You have a trusted party that is validating both chains. So you have a custodial bridge, and that's fine. Custodial bridges can be quite useful. You have a nice multi-sig, you have a few trusted party, they monitor what's happening on chain A, they monitor what's happening on chain B, and then they'll do transfer between the two of them. You have a lot of centralized services like this. That's totally fine. What's not fine is when they present themselves as somehow offering more securities in this or being decentralized. And that's a lot of what you see with like super chains and all of this type of technologies. They fundamentally are trying to do something like that. And it's been tried. People have talked about scaling for a long time, and the idea of scaling with multiple chains that would talk to each other in some ways. And like every single time you have these chains talking to each other in some way, not every single time, but most of the time, you'll find some sort of centralized custodial party that does this. So Etherlink, let's talk a little bit about that, because it's we have a preview that's launching on mainnet for integration partners. Etherlink is an EVM compatible rollup built on top of Tezos, so it's fully compatible with Ethereum, and it's launching on top of Tezos. It's a rollup, and it's a real rollup. We like to be very stupid. So the stupid thing that we're doing is like we build a real rollup. It doesn't have it's not custodial. Like every single rollup today that exists on Ethereum is custodial. There's a set of keys that can take all the customer funds. If you are keeping your assets on the base rollup from Coinbase, it is exactly equivalent to being in Coinbase custody. Coinbase custody is a great product. Yay Coinbase custody. However, it's not different from Base. They have complete access. They can take all user funds. They have a signature to do that. So it's weird to call this, a rollup. Today, there's not a single rollup that's been decentralized, and I think that changes with Etherlink because it's not custodial. It also has a decentralized sequencer. People are going to quibble as to what a decentralized sequencer means. So it is decentralized in the sense that no one has any de jure right to be the sequencer. The sequencer is elected on chain. Anyone can be a sequencer. However, it's a single node. So it's a single node that can be elected and replaced, which is important because it prevents monopolistic abuse, for example, around fees, like we've mentioned before. However, it's not distributed. It's much more important to be decentralized than to be distributed. The minute you distribute it, you start losing a lot of the latency benefits. And so you see a lot of distributed sequencers that sell themselves as being decentralized, but actually they're only distributed. High throughput, low fees, and one thing that we've been working on, it won't be for the preview, but it will be for the full launch, is MEV protection. We didn't invent it. It's basically threshold encryption of transaction, but the threshold encryption of transaction means that your DeFi trade is not going to get sandwiched, which is great. I would say a lot of the popularity of L2s with DeFi has been the UX, but it has also been the fact that because they've had centralized sequencer and the centralized sequencer pinky swears that they're not going to extract MEV from you, essentially it's been much better for DeFi traders, but that is based on a pinky promise and not on cryptography. Yeah, and we have, I think, 5 minutes for a Q&A. All right. Any takers? Yes. Yeah, so the question is how to load balance, how do you load balance sequencers if there's like a lot of demand? It depends where the demand manifests. I think the first thing is that you need to have a good fee model, right? So the way that blockchains deal with congestion is pricing. And the model here is inspired by Arbitrum. Essentially, if you start having too much gas that gets executed over a period of time or too many ticks inside of the rollup execution engine, then you start raising fees. And if you don't have enough, then you start lowering fees. So you have dynamically adjusting fees so that it costs money for people to just put in too many transactions and it rises very, very quickly. So that prevents having too many valid transactions being posted to you. That doesn't do the full load balancing because you could also have a lot of invalid transactions sent to you, transactions that can't pay their fees. So a very important thing, and it's been a key aspect of L1 development on Tezos for the past few years, I think it's one of the overlooked part of engineering, is the most important thing is making sure that transactions pay fees, and you want to have a very quick way of determining whether a transaction can pay its fees or not. That's the first thing. Once it can pay in fees, you don't care what the transaction is, whether it's going to work, whether it's not going to work. Once you know it pays its fees, it's not going to cause you a DDoS because your fees will adjust automatically. And then you could have transactions that can't pay fees, but maybe it's just they're flooding your front end just in terms of like HTTP requests, for example, if you are getting them over an RPC. So, but then you get into much more traditional web engineering in terms of that. I don't think the load balancing helps all this much, because at the end of the day, you still need to focus on one order, and even getting consensus is not going to help you. You're not going to fundamentally balance that. But for a computer, arranging thousands, tens of thousands, even hundreds of thousands or millions of transactions per second is not fundamentally like that. It's not unmanageable as a load. You need to make sure that it doesn't grow without limit, but it can be done. Most of the bottlenecks that you see on this type of things are more about I/O, and again, you want your sequencer to be able to make decisions without relying on I/O. You want to be able to like accept transactions and set your fees, and then later down the pipeline, you actually execute a transaction, gets a result of the transaction. Yes.
Tezos, sorry, that lets it have non-custodial bridge, but not in Ethereum.
Well, what's special is that we don't have it. I think it's what's special is a ideological commitment to not do that. Now, that's a cheeky answer. There's a more generous answer, which is that if you're building a rollup on top of Ethereum, you are building your rollup in Solidity. It's complicated to write a state machine for an optimistic rollup. It's very complicated work, and you have to do all this in Solidity. Now, imagine that you are Arbitrum or Optimism, and you wrote your entire system, and you realize that it's very complicated. Maybe you made some mistake. And if you made some mistake, you can't fork Ethereum to save yourself. Like, you need to upgrade your contract. You need to fix your bug. And that's the best case scenario in which you're the first to catch a bug. Maybe someone else catches a bug. And as a result, because of the complexity of those contracts, they end up having this kind of backdoors. They end up all having multi-sigs that allow people to upgrade them instantly. So despite the fact that they have the security models, there's just not enough confidence in the validity of these contracts, and it takes years and years and years and years to have this confidence. Whereas the Tezos the rollups in Tezos are enshrined, so they're really part of the protocol. First of all, it means that the rollup engine was written directly in the core protocol, so it's much nicer environment to write something like this. You're writing it, we're writing it in Nocamo, but you're writing it with modern tools. It's like, you don't have to basically dance on the edge of the volcano and try to implement this in Solidity, which is not a language that was made for implementing something complex like that. So you have much better language, but also you have the properties that if you have a problem in the underlying rollup engine, God forbid, you still have the opportunity to fork. Like forking out of like critical bug is a very, very neat features that L1s have. You don't want to do it. Like, you don't want to overly rely on it, but it's really nice to know that it's there. And if you are Optimism or Arbitrum, you don't have that option. And that, I think, is like, that's why they basically like have those backdoors, and that's why they keep them for so long, because of the inherent complexity. So that comes with like whether or not you're a first-class citizen in a protocol or like someone's application. I think that's one of the key difference. Yes. Is to have one single rollup. I completely agree. You don't want to have multiple rollups. People think of rollups as a way to scale horizontally. I think of rollups as a way to scale vertically. So now the solution to fragmented liquidity, and one solution is that, well, liquidity will move, like people will trade primarily where there's most liquidity, and then people will add liquidity primarily where there's more trading. So essentially you have like a natural concentration that happens on its own, which is like great for incumbents, not great for competition. But the other force on the opposite end of that are DEX aggregators, where you send to a DEX aggregator, and the DEX aggregator will dispatch to all the chain that have some liquidity. So in some sense, if you do that, even though the liquidity is fragmented, everyone's getting the right price, and everyone's getting a little piece of the trading, regardless of how much liquidity that they have. So I think that's a nice, like DEX aggregators have a lot to do here, even though they're slightly. Typically, like there's some amount of centralization that happen with them. It's really about the UX. But again, like my answer to fragmentation is focus on one single rollup.
That's about all we have for now. But yeah, also thanks a lot for coming here.
Thank you.
And so we're going to take about a 10-minute break before we switch to our next speaker. Our next speaker is Stanley. And so, yeah, she'll be in this room. Cool. Thank you.